optical fiber. So these two experiments we will discuss today. So coming to the Brewster, how do you verify the Brewster's angle and how do you perform the lab? So that we will learn in this session. So for that we need a virtual link, right? So I'll give in a chat box so that you can log in to that link. Fine. So or else you can VLab. You can just type VLab so that you can. Okay. So yeah, here is there. So I'll copy this. Okay. Where I will get the chat box. Can I give here? So you can see my desktop, right? So no, parallelly I'm just okay. You can watch and later you can perform the experiment. No, so you can see, right? VLab virtual labs, right? And go to the laser optics virtual labs. Laser optics virtual labs. If you click on that, it will lead to you. So there are list of virtual labs experiments, and today we're gonna discuss Brewster angle determination or verification and numerical aperture of the fiber. So the third experiment was this. So Brewster's angle, how do you verify this? So if you click on that, so there is a first option is theory, second option is procedure, and third option is self evaluation, and fourth one is simulator. So we need these three: theory, procedure, and simulator. So here the theory is given, right? And this Brewster's angle might have discussed in the class. So here you see, so you have basically, so I'll once again briefly explain the Brewster's angle. Okay. So my whiteboard is visible, right? You can see my whiteboard, right?
Yes, sir.
Yeah. So here in Brewster's angle verification, so first I'll just briefly explain the theory. So this is my, let's say, one medium, denser medium, maybe let's say topaz, any crystal you take. So this is a top surface, right? This is a top surface and this is a bottom surface and this is medium 2. So suppose if you consider as a medium 2, it has a refractive index mu2, right? And the medium is topaz. Okay, so now this experiment I am performing in another medium, let's say in an air, and air has, this is the first medium and it has a refractive index mu1. So now what I'll do is and if you draw a normal to this topaz medium, you have it now. It's gone. Okay, I'll draw again. So this is my second medium, T topaz. Refractive index is mu2, and this is my medium 1, and this is my upper surface of medium 2. So now what I'll do is I'll take a normal to this medium 2 and draw a normal, right? This is my normal. And suppose if I incident a light and the light is coming from medium 1 and incident on this medium, the upper surface of the medium 2, let's say, with certain angle. This is my incident angle. Let's say I or theta I, let's say. So now what will happen? And you consider that to make sure that this is unpolarized light. This is unpolarized light. It means it has all components. So basically, I will represent with the perpendicular component is like this, and parallel is like this. That is how we will represent, right? It means it is unpolarized. So when it is incident on a second medium top surface, it will happen. So we know, right? So partially it will reflect back into the same medium. That is a mu1, refractive index, medium 1. So this will reflect back into the same media. So the reflected I'll represent with a capital R, and partially it will refract also into the medium, right? So will refract, and this is I'll show with a small r. So now if you observe these two parts, the capital R, reflected light and refracted light. So the refracted light has both components, parallel and perpendicular, both. But if you observe the reflected light, so it will have only one component, the perpendicular one. So when this is possible, this is only possible the incident angle is IP. That is what the Brewster said, right? So what is the formula? Tan theta P is equal to mu2 by mu1. So when the incident angle is theta I is equal to IP, theta P, then only you will find the reflected light has only one component. It means the other components are polarized. So the reflected light now I can call it as a plane polarized. This is a plane polarized light now. So when it happens, when the incident angle is equivalent to the theta p, then only you will see the reflected light is plane polarized. So how do you verify this? So if you put a polarizer here, let's say, if you put a polarizer, suppose this is a reflected ray, if you put a polarizer here, then, so these are the perpendicular components, right? So if you take a parallel polarizer, then the perpendicular components will be stopped with this polarizer, right? So the outcome, you never see, no, so you don't find any light, no light. Because this is parallel, so the vibrations of this plane polarized lights are perpendicular, right? So the polarizer will stop this components. So you will not see any light the other end. The polarizer will completely polarize all components. So no light. So then we can confirm that the reflected light has only one component. That's why we will call a plane polarized. And that will happen only the incident angle is equivalent to IP. So if you put that IP and apply the tan, that is equivalent to mu2 by mu1, because this IP theta p is directly proportional to the mu2. That depends on basically what is the medium you are considering, second medium, in to that refractive index only. Okay, so but how do you confirm, how do you verify this? What is the angle so that you will get the plane polarized light? So that is what we are going to verify in this experiment. How do you verify that theta p? And for particular this second medium, what is the theta p? Okay, right. So for that, so if you go to the procedure, so here you see, so here the how do you proceed to perform this simulator? There is a procedure given. So performing the simulator, how do you perform? So first, drag the components from the right panel and place them correctly in the optical fiber. So if you click on this simulator, so here you can see the simulator. Is it fine? Can you see my screen?
Yes, sir.
Yeah. So here the simulator part is open, and so the top part we have a few operators or apertures. One is a emitter, another is a current output unit, and detector, polarizer, and material holder. And below you can see a optical bench, right? And if you click on any one of this, so here the optical bench has a few boxes, right? 5 boxes. So you have to drop these apertures or operators or components in a right place, because initially we have to have a source, right? And this source will emit a light. Then you have to go to this polarizer, and next detect material holder, right? So you have to have a medium too, second medium. So it will hold the medium, whatever the medium you choose. And next detector. Then this detector is connected to current output unit. So this is the way one has to arrange the experimental setup. So that is in the procedure you can see that is given. So if you follow this procedure, it is very easy how to handle this simulator. So first drag the components from the right panel and place them correctly in the optical bench. And next, start. Start is there. So this button enables the user to start the experiment. So if you arrange these apertures in a right way, then automatically this start button will enable. And you have a side view, top view, choose light, choose medium, choose material, switch on light, angle of polarizer, angle of incident, and reset. So these options will enable automatically after the arrangement of this simulator. So once again, I'll show you how to set up this, then polarizer, this box, then
Sir, material will come, sir.
no, I'll show you material where it will come. I'll show you how to choose the material. I'll show you. So now, sorry. How do I go back?
Sir, click on Firefox icon, sir.
Okay. Oh, thanks. Thanks. Right. So, but I see the, yeah.
Sir,
Okay, right. Right. So now you can see my full screen, right? So
yes, sir.
now,
Yes, sir.
now if you arrange all these components in a right manner, then right side on the top, you can see the variables, right? So here the variable is enabled. And here you can see side view, top view, choose the medium, choose the material, switch on light, rotate glass plate, show result, reset. So these are the options given in the procedure, right? And those options are enabled once you arrange in a right manner. Now our job is, so this is a side view of the experimental setup. Suppose if I click on a top view, so the view is changed. So you can see from the top. And here, where you want to perform this experiment. So let's say choose a medium. Which medium you want to perform? Basically, we will perform in air, right? Because when you do in a lab, around you, you will observe air, right? But in this simulator, there is an option. You can also have a different gases. So air, helium, hydrogen, carbon dioxide. So that up to you, you can choose. But according to that, the refractive index of medium will change slightly. Suppose I want to fix for a air, so click on that air, then mu1 is 1. And choose the material so that here the material will automatically, the material holder will pick up that material. Suppose let's say here you have three different materials, topaz, glass, and flint glass, chrome glass and flint glass. So corresponding materials, you have a different mu too, right? So let's say topaz I'll choose. And next option is I'll switch on the light. So if you switch on the light, because here I have selected as a top view, I could not see anything, right? So if you choose a side view, then you can see. So light is on, and this light is passing through this polarizer, and it is focused on a material topaz. So I do not know what is the angle of this incident light so far. So it will incident, and partly it will reflect and partly it will refract. So the optical bench has certain arrangements. Where we want to focus? We want to focus the reflected light, right? So if you focus on a reflect light and the setup is such, the reflected light outcome is connected to this photodetector, and photodetector is connected to this current unit. So how much light is entered to are reflected from this topaz material, and now this reflected light is passing through this polarizer, and from that it is connected to the photodetector, and photodetector is connected to current unit. So the light, how much light is converted as a current. So basically what I explained is we are focusing on a reflected light, right? So reflected light is if your incident angle is theta p, then you will observe no light, right? No light means, so we will see that one. We will see by performing the experiment, we will see. So now what we have to do is here on a top view, on the top you can see one glass plate, right? So the material you can rotate, right? The holder you can rotate so that you can adjust the incident angle. And if you rotate, and how much you have rotated, that can be indicated by this micrometer. Okay, and how much you are rotating also you can see here, rotate glass plate. So how much you can rotate, you can see here, minus 74.7 degrees, and you can keep on increase, and you can also see the current in this unit. So suppose if I start increasing, you can observe, right? There is a slight change in current. Current is decreasing because it is -2 plus it is moving. So current obviously will decrease. And if I still increase, rotate the glass plate. So here you can see the material holder, the glass plate will rotate. How much I am rotating, you can see from the top view, and you can also see from this variable, rotate glass plate variable. So if I go at minus 26.1 degree, your current is 9.97. So if I still further increase the rotations, so it is still increasing, it is still increasing, still increasing. Okay, still increasing, increasing, increasing. Oh, here it is decreasing, right? This is the maximum I thought. And yeah, it is decreasing, right? Means if you put a polarizer to the reflected light, then it is stopping, right? When it is exactly the polarizer becomes a parallel, then the perpendicular components will cut down, right? So you will see the minimum current there, where exactly it is stopping the all components. Not all.
Over there on the digital meter, are we measuring the intensity of the light, or what are we measuring exactly?
Hello?
Sir, in the digital meter, are we measuring the intensity of the light?
This is connected to the photo detector, and photo detector is connected to the current unit. So the light will convert it into the current, and from that, so one can see.
Sir, go on.
Okay. So suppose at what angle? So we have to observe the minimum current actually. Where exactly you are getting the minimum current. So this is 61. Okay, still it is minimum. Zero 1.0019, right? 8 2 0 3 increasing. So this is my minimum current. So at what is the rotated glass plate? What is the angle? So here you can see, right? So this angle is because the theta I is equal to theta P, then you will get the minimum current, means no light. Means that is the minimum current. So at what angle I got this? At 58.1 degrees, right? So yeah, here show result button is there. If you click on that, so here you can see Brewster angle is 58.11. That is accurate, because here I could not go that much minute. 58.11 degree I could not see here, but when you click on the show result, it is showing the accurate result of this Brewster angle is 58.11 degree. So there I could get the minimum. So if you incident with that angle, then the reflected ray is plane polarized. Okay, so this is a Brewster angle for this topaz, right? And you can also calculate this by using the tan theta p is equal to mu2 by mu1, where mu2 is the refractive index of this material, and the mu1 is the air, whatever. So here you have a different options, so you can click and you can verify. So for stone glass, flint glass, you have mu2. Have different you can combination you can choose, and you can calculate the theta p, so that where it is exactly with at which angle it is plane polarized. So how do you get the, suppose if you plot a current versus theta, how does it look like? Suppose if I want to plot a current versus theta, right? So on an x-axis you can have a theta, and on the y-axis current. So how does it look like? So when theta is something, you have a maximum or some current, right? Some current, let's say maximum current. And when you increase the theta, just now we have seen in a simulator, your current gradually decreases, right? It decreases, and at particular theta, it has a minimum value. And after that theta, if you keep on increasing, the current will start enhancing or increasing. So this is the minimum current we got for particular material, let's say topaz. And you have a mu, corresponding mu for this. And if you can calculate, if you can note down the theta p, and it comes to be 58.11. And the minimum current is 1, right? 1.00. And we have two other currents. And this is the behavior of the current with respect to theta. And if you can substitute in the with respect to this also, you can calculate, right? So this is how one can verify for a given material what is the theta p with this simulator. Is it fine? Okay. So now, so you can choose different mediums and different materials, and you can verify the Brewster angle. Now coming to the fourth experiment, how do you calculate the numerical aperture of a given fiber? For that, you have to click this. So go to the VLab and click on this numerical aperture of fiber, optical fiber. If you can click on this, it will lead to this experiment. There also you have a theory, procedure, self-evaluation, and simulator. So assignments, references, feedback, we don't have to go into details. That up to you. You can check them. Yeah. So coming to the numerical aperture of optical fiber. So here the theory part is given, and this theory is discussed. Hello? In the class?
Sir, yes, sir.
Yeah. So it is discussed, right?
Yes, sir. Today morning only, sir, discussed, sir.
Yeah, okay. Okay, very good. Nice. So then, yeah. So then how do you calculate this numerical aperture for given a fiber? So here, if you go to the procedure, so here you see, so here also you have a optical bench, and if you go to the simulator, there also on the top you have a operators you have, and you have to drag those operators into the appropriate boxes. So this is the order from the right to left. So first we have to adjust emitter, then concentrator and fiber, then fiber stand and detector and output unit, current output unit. So this is the way one has to adjust, one has to drag and put into that boxes. Then the options, the variables will enable. So what are the variables? Start button, switch on, select fiber, select laser, detector distance, and detector distance x, one is in z axis, another is in x direction, and show graph and reset. These are the options they will enable once you set up this operators in a right manner. Okay, so right. So now, so before going to the simulator, I'll slightly give a brief theory about this numerical aperture. So coming to the fourth experiment, okay, let's go. Yeah. So now experiment fourth. And this is numerical aperture, right? Optical fiber. Fine. So you know so optical fiber, how does it look like? I'll draw it so that it is very clear. So this side I have, this is a second end, this is a one end. It has two ends, right? And it has two parts. Sorry. So this is a cladding, right? This is a cladding part. Has a refractive index something, let's say mu2 or n2, some people also refer n2. And inside this one is core. This is a core. And it has a refractive index, let's say mu1 or n1. And this experiment we are performing, let's say in A. So outside also you have a medium. So that is mu0. It has a refractive index mu0 or n0. So now it has its own optical axis. This is my optical axis. And with respect to this, if I want to send a light inside this optical fiber, then you know, right? According to the theory, suppose this is my normal. So with respect to this normal, I pump a light into this fiber, let's say with this angle. This is, let's say, I, and so this is only one side, right? So with respect to this angle, I can also form a cone, right? So suppose the other side also you can send a light, right? And with this area you can form a cone. What is the meaning of this? Means suppose if you send a light from within this cone, this way or this way or this way or this way, this way, this way, this way, it will pump into within this cone of the angle. Then when you are pumping the light into this fiber within the cone, then it will take, means it will pump into the core, then from one end to the other end, it will take total internal reflections, then whatever sending your information, it will reach the other end. Otherwise, no. And what is that angle actually? What is the maximum angle? So that it will take a total internal reflections, means this, and it will come out. So what is that angle, maximum angle? So that is what we will gonna determine in this experiment. So once you are sending from the first one end, the same information will come out to the other end, right? But how do you measure this angle? So from this end, first end, measuring the angle, it is very difficult, because you cannot, it is difficult to measure the angle, at which angle you are incidenting, so that it will pump into the fiber, and it will take a total internal reflections and then coming out. But what we can do is, instead of that, if you observe the second end, so when you are pumping with this angle, it will take a multiple reflections, total internal reflections, then it is coming out, right? But you can observe at what angle it is coming out. That you can observe, right? That you can calculate, right? So how do you calculate that? And what is the procedure for that? It is all about this experiment. So in this experiment, we will not consider the first end, we will focus on the second end when it is emerging out. So if you look that angle, the other end also it has a certain angle. Whatever the angle you are incidenting, with the same angle it will come out, and it will also form a same cone, the other end, right? So let's say this is my light coming out. Suppose if you put a screen here, then whatever the light coming out, if you put a screen over here, the other end, opposite to the other end, then how much intensity it has, you can see, right? On the screen, it will form a circular pattern, right? In a 2 dimension, but a 3 dimension it will form a Gaussian. This kind of pattern it has. So in 3 dimension it look like a Gaussian profile, but a 2 dimension on a screen it will look like a circle. So in the middle, when you are in the middle, it has a more intense. When you are going from the center, middle to the both ends, the intensity will decrease. Okay, so how do you measure that? Because here you have, so I'll draw a setup. First I'll show the simulator, then I'll explain this. So yeah, so this is the numerical aperture of the optical fiber. So here you can see the simulator. So once you click on any this, so suppose emitter. So if you want to adjust this emitter, automatically on the optical fiber bench, you can see some boxes. So we have to arrange this operators in a right manner. So first emitter, then concentrator. So when light emits, where exactly we want, it will concentrate. Then after concentrator, we have to pump this in light through this fiber, right? So before that, we need a fiber stand. So this is my fiber stand, and so fiber stand will hold this fiber. So detector and current output and the fiber. So this fiber is between holder and concentrator. So now light will emit from the emitter, and where exactly we want to focus? We want to focus on this fiber. So the light will pass through this fiber, and the other end, the light will come out. And here this is detector is acting as a screen, right? And this photodetector will connected to the current unit, and how much light is coming out, that will converted as a in terms of current. So here also you can have a minimum maximum current, where it is minimum, where it is maximum. Okay, so based on that, we can plot a curve and we can calculate the R and distance between the screen photodetector and the second end of other end of the fiber. Okay, so this is the arrangement. Once you arrange it in a right manner, so there already variables will enable. So here start button is there. If you click on that, so the other variables enables. So here you have select a fiber. So if you click here, so first we have to switch the light on, right? So when you switch on the light, so emitter will emit a light. Then now the all variables enabled. So select any one fiber. So here you have two fibers only, glass fiber, plastic glass fiber. So you can choose any one, X one, and you can also select the laser. Which source you want to use, red laser or green or, let us focus on red. And here you have a detector distance Z, detector distance X, right? And here you have a show vernier reading, because here you have a screw gauge. With that, you can calculate these distances, how much you have moved. Okay, so now we will start how to perform this experiment. So now I want to go to the theory. First, what is a Z? Z means, so from the other end, you can see my whiteboard, right? So this is my second end of the fiber, and this is a photo detector or screen. So this distance is D. Fine, you understood this. This is a D distance. So this distance you can adjust. So you can move this screen front or back, right, towards the fiber or away from the fiber. You can distance, you can adjust, so that you can calculate the D. And so when you pump a light from the other end, it will eject, and on this photo detector, it will form as a sphere, profile, Gaussian profile, right? Then how does it look like? So through this simulator, we will see how does it look like. So here you can see, right? So in a 2D, it will look like a circle, but when you plot this in a 3 dimension, how does it look like? It is a Gaussian profile, right? So if you want to really see how the Gaussian picture will look like, show one, I have a 3D pictures plotted for my research. So I'll show you how they look like. Yeah, can you see my screen? So this is the Gaussian, right? In a 3D. Okay, I'll show in a one MATLAB, then it will be convenient so that I can rotate them. And in a 2 dimension, how do you draw that Gaussian profile? So it look like this. It look like this. That is what I have shown here, right? So here, this in a 3D. But in 2D, here below that, you can see the contour plot in a circle, right? That is a 2 dimension. It is a contour plot of this Gaussian profile. But basically in 3D, it will look like this. So that one I'll show in a effective way. Is it okay? Yeah, so this is a Gaussian profile. Fine? Right. So this is the Gaussian profile look like this. This is my Gaussian profile. Right? So at the center, it has a more intensity. And so this is my center. It has more in maximum intensity here. And when you go away from this center, the intensity will decrease. I will decrease. I decreases. But how do you represent this Gaussian profile in a mathematical way? How do you represent? So the representation is this, right? So this is exponential, right? And maximum at center, and both side it is symmetric, and symmetrically it is decreasing. So the mathematical representation for this Gaussian profile is exponential minus, so let's say this is my x-axis, and so I have to keep this x, and this is parabola nature also there, so x square divided by r square, right? And when this x is equal to r, what you will get? Suppose at x is equal to r, what happens to this Gaussian profile?
e to the power minus 1.
This is e power minus 1, right? If x is equal to r. So, and this is also one can write 1 over e, right? So, x is equal to r means where you will get this x is equal to r at the center, right? So this is, so yeah, and this is a field, right? Light means it is a field. So this field I can represent with E also, right? And this E is maximum at what? The maximum value is exponential minus 1 if x is equal to r, right? And if this is a field, how do you calculate the intensity? Intensity is modulus of this E is square, right? And we want to calculate the maximum intensity. Maximum intensity is where it is maximum at x is equal to r. So E max square, and you have e to the power of minus 1, right? So this is minus, so square, so whole square, minus square. And suppose I want to calculate the maximum intensity. So this is I actually, and I want to calculate the maximum intensity. So this is I can write I by E square, or I is equal to I max by, or other way I can write this way also, right? I is equal to I max by E square. And if you plot the current versus the x distance, then how does it look like? Suppose I want to plot this on a x-axis. I have a detector distance detector distance in X, and on a y-axis I have current I in amps. So yeah, so how do you perform this experiment? Before drawing this, so I'll once again go to the simulator. Here you see, so we have to fix this D. This is in our hand, right? The second end of the optical fiber and the distance between second end of the optical fiber and the photodetector or the screen. That D you fix. And then how do you fix that D in a simulator? So this is a detector distance that you can fix, right? So that you can fix that in your hand. You can fix this distance. And at what distance you want to fix? Suppose let's say I am fixing it 4 millimeter. And now the detector distance X direction I want to move. So here we have a two directions. One is Z and other is X. So how do you confirm this? So let's say here two distances are there. So one is this horizontal, other is the Gaussian profile, because here also you have on a Gaussian profile, if you see this Gaussian profile. So I have said X, right? Or on a screen, you have a circles, right? And this circle from the center, it has a radius, let's say R. So how much radius you want to get? What is the radius of this circle? That depend on how much distance you fix, right? Isn't it? So if you bring closer, if you change this D, the R will change, right? Radius of this profile, Gaussian profile will change, right? Isn't it? Are you okay? Do you agree?
Yes, sir.
Because suppose instead of here, I want to fix here, then it is more intense. But the radius, if you find, radius is very small compared to this. Because when you're going away from this second end of the fiber of optical fiber, the cone will increase, right? Acceptance cone will increase, right? Increasing means radius is increasing. So you will get this much of circle. Isn't it? Okay, so these are the two variables. That's why there you can find a one triangle, isn't it? So, or either maybe the upper side or lower side, you can form a triangle, and you know this D, and you know the R, and you can calculate the angle. You understood? You can calculate this angle actually, because here you will see. So I'll draw with a red mark. So this is my center, and this is my angle, and this is my D. This is my D, right? Actually, this is my D. This is my R. This is my theta. So from sine theta, you can always calculate this R. And how do you write this from this triangle? Sine theta is equal to the opposite by adjacent, right? So R by under root of this. How do you measure this? This is in terms of R square plus D square. So once you can calculate that theta, then theta is equal, once you calculate the sine theta, and theta is equal to sine inverse R by R under root of R square D square. And this is what we are interested. This is we call a numerical aperture. And you might have derived the numerical aperture as a in terms of mu0, mu2, mu1 also, right? That is sine inverse square root of mu1 square minus mu2 square by mu0. That is also a formula. Acceptance angle. And numerical aperture is sine theta, whatever the maximum angle. So how do you now you see there is a change in current, right? When you change the x, there is a change in, means the Gaussian profile, there is a change. So the intensity focus will change, right? So now we have another, so how much distance you have traveled, that you can observe from this screw gauge. So you know the screw gauge, how to measure the distance, right? The help of screw gauge. So the screw gauge is given here. It has a head scale and pitch scale. So you know the least count for that. So I think in the previous, in the beginning in the lab, Uday sir might have discussed about this vernier calipers and screw gauge. But anyway, you can look into any video and you can calculate that distance. But here we have another option. Show graph, the last option, last but one. So if you click on that, there is a current versus detector distance. So if you keep on increasing this, then there is a current versus distance x plot you can see. Or you can note down this distance and the current, you can also plot. But a plot automatically the option is given. It is up to you. You can plot with your hand, or you can suppose fix here, note down the current, then move some distance and note down the current. So how the current behavior with respect to x you can observe, right? Always. So, and that is with this option also you can see when you start increasing the detector distance x, Up to 6 millimeter, it is 0. But when you move further, it is start increasing. At 9, it reached to maximum, and from that value, it is decreasing. So with the help of this plot, one can calculate the R. Sir, how do I calculate the R? So here comes the explanation. So when you look this Gaussian profile, where x is equal to R, it is maximum, right? And we have seen this x is equal to 9 is equal to, at x is equal to 9 millimeter, it has a maximum intensity. And this x is equal to 9 is equal to 9 millimeter is a maximum. And so in the graph, this is my, from this end to this end, this is actually 2R, right? And this is my R from the center. This is my R, this is my full length is 2R. But how do I calculate the R? So at x is equal to R, the intensity of the light is maximum. So that I will take it as a starting point. And here we have derived one formula. I is equal to I max by E square. Isn't it? I is equal to I max by E square. So I is equal to I max by E square, where E is equal to 2.7, that value is there, right? But in your theory, it is given wrongly. So if you can notice, yeah. If you go to the theory part, there is some okay, so here procedure maybe. And yeah, here you can see, right? So this is I max by 2.71 they have given. Actually, it is I max by E square, right? According to this formula. So that you have to correct. So this is I max, and I max by, so this is actually 2R. And if you take the one side, so where you want to focus? Suppose I want to calculate a R, let's say. At a distance, I max by 2.71 square. Let's say at this value, let's say. Adjust again. Anyway, problem. So if I arrange wrong way, it will not come. But just, so this is concentrator, right? So it's to be here. Then detector, this is current unit, fiber. Okay. So now if you start, yeah. So at 4 I have fixed, right? Jump 4 and show graph. Yeah. So maximum it is coming with a distance 4. With a distance 4, maximum you can find at 9, right? But I max by E square, suppose I want to calculate here at 11, let's say 11. So I max by E square. So this is my 9, this is 9. At 11 I want to calculate. So this is my 11. So this is my I max by E square. This is at 11. So I'm interested at this. And this is my 2R. So how do you get the R now? This is my R. So 11 minus 9. This is my R. So you know the R. This is your R. And you know the D. And if you substitute in a sine theta, and you can able to calculate this theta. But this is not full theta, right? If you can observe the acceptance angle, this is not the full theta. This is half. So this is only half result because this is not the full theta we have considered. This is only just theta, half theta. If you want to consider full, you have to add 2. You want to multiply 2 into 2. And that is we call numerical aperture. And this is a way to calculate with the help of this simulator. But it is when you are present in the lab, this is also same, same you will do. So here we have a screen, and the screen has a certain circles, and the circles already measured, means they have particular distance of circles. So if suppose if you want to coincide with the first circle, it has a certain diameter. Then if you half it, you will get the radius. So, and where you are exactly putting your screen so that your light is light profile is coming within that the first circle, and first circle has a certain diameter in millimeter, and you have fixed the D, right? So you know the D, you can calculate the D with a scalar, with a vernier caliper, with a screw gauge, and this is the numerical aperture. So with this, we today we have discussed how to verify the Brewster's angle and the numerical aperture of optical fiber. Okay, thank you. So, is there are any questions?
Sir,
Yeah.
how many cases for that Brewster angle experiment, sir?
Yeah, that because it is up to you. I do not know. You have to, because how there are so many to back. How many mediums are there? Are 3 you can do maximum. 3 you can choose. You can choose.
Okay, sir.
3. It is very easy, right? Just you have to vary the theta, and in the below also you have the option, right? Below you have so yeah, so measurement, you can click on measurement, show result, so it will show. First, suppose, yeah, we have first media measure 4 options, right? And material, Material 3. So many combinations will come.
Yes.
Yeah, many combinations will be there. But I don't know. So you can do for 3 combinations. That's it. That is good enough. Okay, once you can choose A, then helium, hydrogen, carbon dioxide. So with the 2, 3 are good enough because it is boring, right? 2, 3 is good enough. Maximum 3 you can. Maximum 3 combinations you can go. Okay. Right.
Okay, sir. Thank you,
Okay.
sir.
Thank you. Okay. Thank you so much.
Thank you so
Thanks.